So here's what you need to know about Le Chatelier's principle. Henry Louis Le Chatelier is the scientist from France. He developed this principle, so that's why it's called Le Chatelier's principle, aka the equilibrium law. You can call it Le Chatelier's principle. You can call it Le Chatelier's principle. Pronunciation doesn't really matter here. It's AP Chem, not French. Anyway, Le Chatelier's principle officially states that when a system experiences a disturbance, such as concentration, temperature, volume, or pressure changes, it will respond to restore a new equilibrium state. Equilibrium is when the rates of the forward reaction are the same, meaning that the same amount of product is created as the same amount of reactant is consumed. Let's look at a reaction that contains variables for simplicity. A and B are your reactants, and C and D are your products. The double arrows mean that the forward and reverse reactions are moving at the same rate, indicating equilibrium. Let's say you want to add more of A, which is a reactant. Since you added more of A, the reaction will shift toward the right to make sure that the corresponding amount of reactant is increased. When the sufficient amount of product is created, the reaction will go back to equilibrium. Conversely, if you were to add more product, such as C, the reaction will move to the right to produce more reactant until the reaction is at equilibrium again. To put this in terms of a real-life example, basically think of two kids on a seesaw. If you have a heavier kid sitting on one end of the seesaw will be lifted in the side that the lighter kid is sitting on and go down on the side that the heavier kid is sitting, and vice versa. Temperature also acts in the same way. For endothermic reactions where temperature is absorbed by the reaction, the heat of reaction is positive and therefore can be considered a reactant. If you increase the temperature of the reaction, it's like increasing a reactant, and the reaction will move in the opposite direction. If you decrease the temperature, it's like decreasing a reactant, and the reaction will move toward the reactant side. For exothermic reactions where temperature is released by the reaction, the heat of reaction is negative and therefore can be considered a product. If you increase the temperature, it's like increasing a product, and the reaction will shift in the opposite reaction. If you decrease the temperature, it's like decreasing a product, and the reaction will move toward the product side. Pressure and volume are closely related, but they only need to be considered if the amount of moles of gas on both sides of the reactants are different. Pressure and volume don't affect equilibrium if moles of gas are the same on both sides, or if there are only solids, liquids, or aqueous solutions in the reaction. Let's take a look at the Haber process, which is a real-life industrial reaction that is used in the production of ammonia from nitrogen and hydrogen. There are 4 moles of gas, 1 of nitrogen and 3 of hydrogen, on the reactant side, and 2 moles of ammonia on the product side. If the pressure of the system is increased, that means the volume is decreased, so the reaction will move away from the side with more moles of gas. If the pressure of the system is decreased, that means the volume is increased, so the reaction will move away from the side with less moles of gas. So for the Haber process, if the pressure is increased, the reaction will move towards the product side, and if the pressure is decreased, the reaction will move towards the reactant side. Now let's talk about Q and K. Kq is the equilibrium constant. The equilibrium expression is the concentration of aqueous products over the concentration of aqueous reactants at equilibrium. Kp is the pressure constant. The equilibrium expression for Kp is the partial pressure of the products over the partial pressure of the reactants. Solids and liquids are not included in equilibrium expressions. Q is the variable used to determine the reaction at a point that is not considered to be an equilibrium. The expression rules are the same. Let's say that you find that Q is greater than K. That means the concentrations or pressure of products of Q are greater than that of the products of K. The reaction will then have to shift to the left, toward the reactants, to make the values equal for the reaction to be at equilibrium. Conversely, if Q is less than K, that means the concentration or pressure of the products at Q are less than that of K. So the reaction will shift to the right towards products to get Q equal to K. Thus, if Q and K are equal, the reaction is at equilibrium. And that's basically all you need to know about Le Chatelier's principle.
Yeah, they shift and they shift and they shift and they shift and they shifting for me. Yeah. Reactions moving calm, don't start no trouble with it. Stay at equilibrium is a struggle for it. Add some more reactants just to shift to the right. You know how it likes it when the rates are the same. Add some more reactants, products increase. Yes, I see the species that are shifting on me.
How'd I get this reactant to decrease? Just remove some product, yeah, it's easy.
Shots plan. Shots plan. Reaction moves forward, sometimes it won't. Reaction will reverse, sometimes it don't. I increase that temperature. Products might go up a bit. I go hard on ICE. I make sure equilibrium is achieved. And still, chem things. It's a lot of chem things used for shift, and they shift, and they shift, and they shift, and they shift, and on me. Chem things. It's a lot of chem things used for shift, and they shift, and they shift, and they shift, and they shift, and on me.
Yo, hey. She said that you shift me, I told her only partly. If Q is greater than K, reverse favored, I'm sorry. Chatelier, I even got it tatted on me. Greater K brings more products to the party. And you know me, make the Q the same as the KC. Different K and Q equals not achieved. They're the same, equilibrium's achieved.
Shots plan. Shots plan. Volume's pretty low right now. Pressure's really going up. Put the two together now. Shift into reactant side.
Pressure doesn't change a thing. And moles on both sides are the same. Still.
Chem things. It's a lot of chem things. These are shift and they shift and they shift and they shift and they shift and on me. Chem things. It's a lot of chem things. These are shift and they shift and they shift and they shift and they shift and on me.
Cry now.